Hello, welcome to the CDB Technical Introduction. In this module, we'll be introducing you to the basic theory and architecture of the CDB database, which is pre-integrated in ConfD. In a subsequent module, we'll take a look more at working on CDB subscribers and programming for CDB. The CDB database in ConfD is a hierarchically organized database, meaning it's tree-shaped. This goes very well since we are working with Yang data models in ConfD because Yang data models are hierarchical and tree-shaped, so the organization of the database naturally matches the organization of the data models. CDB is memory resident, and it also uses the file system to save the contents of the database in the file. So as transactions commit to CDB, the in-memory contents are updated, and then journal entries are appended to the files in the file system. CDB supports replication for high availability environments. It supports automatic schema version changes, upgrades, downgrades based on data model changes that ConfD is running. CDB can also hold your configuration data, or it can also hold your operational state data, and it's totally up to you in terms of what data you put in CDB. You can also use an external database in addition to or instead of CDB. CDB does support automatic loading of initialization data. You can provide XML instance documents which match the schema of your Yang data models, and ConfD will use that to initialize the CDB values when it first runs and creates the database. Your applications, when they're working with CDB, will initially come up, read their configuration from the database, place subscriptions which tell CDB if this area of configuration data changes, please notify me of the changes. Those subscriptions support having priority levels assigned to them so you can control the order in which your subscribers are notified. Also, CDB contains multiple data stores as driven by the netconf standards. There are the concept of startup, running, and candidate data stores in CDB. These are transactional data stores which can hold your configuration data. The fourth data store is for operational data. It's an atomic data store because the atomic model matches the needs for storing operational data better than a transactional model. So, CDB is hierarchically organized. If you've worked with relational databases in the past, such as an SQL database, relational databases tend to be just flat. It's just tables, and you access different tables. In a hierarchical database, it's truly tree-shaped with a hierarchy that you move up and down. Oftentimes, I'll talk as if CDB has just one tree in it for ease of explanation. However, you have multiple Yang data models in your system. Each Yang model is a namespace and hence its own tree, all within CDB. So here on this slide, we have an example of a hierarchy where we have a top root and then different branches off of it. This model of hierarchical data representation actually naturally matches the model of configuration data. So that hierarchical organization is ideal to use when working with network management configuration data. If we had to work with the hierarchical Yang data models and store them in a traditional relational database, we would get into issues of object relational mapping, of how do we map different levels of our hierarchy into these flat tables of a relational database. So as a result, we get better performance in a cleaner architecture from using a hierarchical database. Now, I'd mentioned that CDB has multiple data stores and that some of them are transactional. CDB is a transactional database, just like the rest of ConfD is a transaction. Transactions in computer science theory have certain properties they must meet in order to be considered a transaction. These properties are known as the acid properties: atomicity, consistency, independence, and durability. Atomicity means transactions are indivisible. They're all or nothing. They either succeed or they fail. You never end up at some unknown, intermediate, inconsistent state. They succeed or they fail. They're atomic. The second property is consistency. Transactions are all at once, meaning order doesn't matter for a transaction. Whether you create A and then create B in a transaction, or you create B and then A in the transaction, the end result is the same. From your starting point to your ending point, all paths are equal. Order is unimportant. Third property is independence. Transactions do not interfere with each other, meaning a transaction is its own atomic unit. It succeeds or fails, but two transactions cannot interfere with each other. They're self-contained units, and one transaction will commit on its own without another transaction committing in the middle of it in order to provide that independence. The fourth property of transactions is durability, meaning they persist. You commit a transaction into the system, it succeeds, that change is persistent. It's stored. So, the ACID properties must be met by any transactional system and are met by the CDB database and also ConfD overall in its transactional processing. Database storage. I mentioned CDB is both an in-memory database and also persisted to the file system. Here we see a basic representation of that storage. The CDB will be in memory for fast processing, ease of use, but then it also needs to be persisted to meet the durability requirements of a transactional system. CDB is not just a file that's seeked back and forth on the file system. Like any modern database system, as transactions commit, they are appended as journal entries to the end of the CDB files in the file system. Periodically, if there's a certain amount of stale data, like any other journaling database, the database will be rolled up and compressed onto the disk, and then journal entries will be further appended to it. There are different options to control the compaction that you'll find in the ConfD User's Guide. Now, as I mentioned earlier, the data model is used to drive the schema of the database. So when ConfD starts up, the data models are loaded. We check the current schema of the database against the data models, and if there's a difference, the upgrade transaction will be initiated. As part of that processing, the database schema will be updated to match the new models. Now, the database also supports replication. You can have one active and any number of standbys, and CDB can be replicated from the active ConfD to any standby nodes. There are some different options available for this replication. The replication can be synchronous or asynchronous. In asynchronous replication, a transaction is committing on the active node. The replication information, which is actually just the journal record entries for CDB, are sent to any standby nodes, and the transaction continues to commit on the active node. On a synchronous replication, that replication of the journal records is sent to the standbys. Then the active ConfD awaits for all the standby nodes to positively acknowledge that they have received the updates, and then the transaction finally commits. So you can do fire and forget replication on the theory that any failure at a standby shouldn't affect the active, or you can do the synchronous and get assurance that it has been replicated to the standby node. ConfD and CDB do things such as heartbeat and monitor that replication link to ensure that the nodes are in contact with each other. If problems do occur, they'll be reported to the external high availability framework, which is setting up the high availability replication relationships and monitoring for any issues that may occur. Now, when CDB starts up, when ConfD boots, CDB's contents are blank at this point. How does the database boot and the system start up? So, first, ConfD will read the data models from the disk. Also, the schema for the current database will be read up. The schema has been stored, is loaded, is consistent with the data models. So, our steps are read the schema of the existing database, start a transaction, read up the current data for the CDB database from the file system, double check that the data from disk is consistent with the data models that we've started this run for. If there are differences, trigger an automatic upgrade scenario that we'll talk about in a moment, and then finally validate that data and commit it into the in-memory copy of CDB. Now, CDB doesn't really differentiate between upgrades and downgrades. It just knows that there's been a data model schema change. An upgrade, downgrade is the same thing, handled in the same way. However, to us, we may semantically consider it an upgrade or downgrade based on the versions of models that we're using. Now, during this automatic schema upgrade, if there has been a data model change relative to what CDB was last run with, we'll start an upgrade transaction to update the schema and the contents of CDB as a result of that data model change. There are many things that we can automatically populate into that upgrade transaction based on analyzing the data model differences between the old set of models and the new set of models. So, some of the examples are shown here on this slide. For example, you've added new default values to your data model. You've removed elements from your data model. You've made simple type changes such as changing a 16-bit integer to a 32-bit integer. So those sorts of simple changes that CDB and ConfD can detect are automatically populated in the upgrade transaction. For more complex changes that we can't automatically handle, there are mechanisms which you can attach an upgrader client to that upgrade transaction and participate in it as part of the data model change and the database upgrade. As a development tool, there are ways of effectively dry running a upgrade scenario to see what changes ConfD is doing automatically, but there is further information on what ConfD can do automatically during that upgrade scenario in the user's guide. The developer's log, most commonly stored in a file called devil.log, will log information about the upgrade, and you can use that to help design if you need to write an upgrade client and what it needs to do. Now, for the upgrades that CDB and ConfD cannot automatically handle as a result of that data model change, you may add your own upgrade clients. What will happen is your upgrade client application will be started. It will attach to that upgrade transaction during what is known as start phase 0 of ConfD. It will be notified after ConfD populates the upgrade transaction with everything it can do automatically. Then your application be notified, can attach to that upgrade transaction, participate in it, add new values, change values that have been automatically computed, and then when your upgrader client is done, ConfD will commit that transaction into CDB and the upgrade has been done. If you make cautious, pragmatic changes to your data models, you may avoid the need to write one of these upgrade clients. One of the nice things about this feature is actually productivity benefit for engineers. You may be working along developing your model, developing your code, and suddenly you realize you need one new configuration value. If you just add it to your model, give it a default value, you just restart ConfD and keep going. There will be no need for you to spend time writing database conversion code as a result of the change. Also, These schema upgrades from the data model changes can be done when ConfD is restarted and done essentially a cold boot, or there are also in-service update mechanisms available for updating data models and the database schema. For the information on the in-service update, please consult the ConfD User's Guide. Here are a few examples of schema upgrade. For example, you're changing a 32-bit flag field to a 64-bit flag field. All the new flags that have been added in that new 64-bit value should be initialized to 0. The automatic upgrade support in ConfD will handle this for you. You've added a new MTU field, but you need that to be 1500 for any of your Ethernet devices and 48 for any of your ATM devices. So in that case, you should use an upgrader client because it needs to make an intelligent decision about the values of other fields in the database in order to compute the value for this new field. In a case of you're changing, say, a type from a string to an enumeration, if any string values that are populated in the database, that string matches the enumeration name, those can be automatically upgraded. However, if there are any string names that don't match the enumeration name and you want those set as part of the upgrade, then you'll need an upgrader client in that scenario. Say we had a time field that we've changed from seconds to nanoseconds. There, you should use an upgrade client because it'll need to read the old value, multiply by 1,000,000,000, and overwrite then the automatic promoted value because really those units were just numbers, so the automatic upgrade just sees the numbers. You need to do that multiplication to do the units conversion yourself. CDB, as we mentioned, has multiple data stores in it. Here we see a slight representation of them. There are up to 4 data stores present in CDB. Startup, running, and candidate hold only configuration data values. The definitions of startup, running, and candidate are driven by the netconf RFC standards. Each is a full copy of the configuration. Their definitions are, running reflects the current running configuration of the system. If startup exists, it is used when the system starts up. Candidate is a future candidate configuration of the system. These ideas of these data stores are supported in CDB, or they also could be mapped and provided by an external database. It's up to you on how you configure the system for whether ConfD uses CDB or that external database. You can split your running configuration between CDB and external databases in combination as well. There is also a few combinations that are legal in terms of how you turn on the data stores. So typically people will have either just running or running and startup or candidate plus running. Oftentimes if you have candidate plus running, you'll set running as writable only through candidate, meaning any changes to running must go through the candidate data store. This does have optimization benefits in that mode. Candidate doesn't need to be stored as a full copy of running. It can simply be a list of deltas against running. The 4th data store in CDB is the operational data store. This is an atomic data store that you would use to store any operational data in CDB in a push mode. Now, the configuration data stores are transactional. They can only be written through a transaction, typically through the management agent API or driven by a northbound interface, through a transaction running in the core engine, and then into CDB. The CDB APIs allow for reading of configuration data from CDB, but the writes must go through the management agent API. Operational data, since that's an atomic data store, does not need to go through a transaction in the core engine. The CDB APIs provide support for your application to write directly to the operational data store in CDB. There are some pseudo-transactional mechanisms available when working with operational data in CDB to have advisory locking, and there are also subscription mechanisms that are available when working with operational data in CDB. So, for the data stores, startup, if it's enabled, is the startup configuration of your system. If your system restarts or boots, whatever, that startup, the contents of the startup configuration data store are copied to the running configuration data store, overwriting the running. It becomes the running configuration on startup. So much like when you work with many Cisco devices, you'll copy running to startup. That startup is your configuration when you start the system. If you don't have the startup data store turned on, whatever was last in the running data store becomes your startup configuration. Now, if the very first time you're starting up ConfD on a system and the CDB files aren't present in the file system, as part of creation and initial population of CDB, ConfD will read from your file system, from the directory where you store CDB, XML initialization files that are used to provide initialization values for CDB. Also, there are ways to use these XML files during CDB upgrades. As I've mentioned, the running data store holds the currently running configuration in the device. And then candidate is a persistent data store of a candidate future configuration. You will make changes into candidate and then commit it as a transaction into the running data store to make it the new system configuration. Now, the life of a typical transaction in regards to ConfD and CDB. So, you'll start a session by logging in, whether it's a CLI login, the initialization of a netconf session. You're typically, say if you're in the CLI, you're in operational mode, you may be showing things, displaying those values, looking through them, and then enter configuration mode and start populating values into a transaction. So you'll be populating changes into that transaction, then you'll want to actually commit those changes. So at the point that you commit them, the engine of ConfD will take locks on the appropriate data stores to ensure that only one consistent set of changes is happening. We will lock, then we'll run semantic validation, meaning any Yang must statements, uniqueness, any of the constraints modeled in your Yang data model are automatically checked by ConfD as driven by the definitions in your Yang model. Also, if there's been any external validation code registered with the system, that validation code will be called, and as long as all the validation passes, then we'll move on to the actual prepare and commit phases of the two-phase commit transaction. We'll wait for acknowledgement from standby nodes if there are any replication in place in synchronous mode. It will inform any CDB subscribers of changes that have been affected. Once all of that completes, then the lock will be released and others can then make write changes into the data store. This next slide shows the state machine of a transaction in ConfD. So you'll typically be sitting in the start phase is where you'll begin. Once you've logged in, you've gone into config mode and are starting a configuration transaction, you go into the read state. In the read state, you're populating the transaction with changes, but the reason we call it the read state is here you may be going out and reading current values and displaying them from configuration or operational data as you're deciding what changes you make. There can be any number of transactions in the read state simultaneously. To ensure stability and robustness of a system that is transactional, though, once we start to commit transactions, we must provide that independence of transactions from the ACID properties and ensure that only one transaction is actively changing at a time. So once we're done populating a transaction and we move on to validation and commit of those changes, we'll make the transaction lock transition, run semantic validation, and then go into the write state in which the data is made available to any external database handlers or to the handlers for CDB, and then do a traditional two-phase prepare commit phase. If you're not familiar with a two-phase commit in transactions, the prepare state, the data is provided to anyone participating in the transaction. They are not supposed to take those changes live. However, they're supposed to look at them and positively acknowledge that, to the best of their ability, to determine that if they tried to take these changes live, it would succeed. Once we hit then the commit phase, and everyone's told to commit, that transaction is committed, it's taken live, it's persisted. There's no way to abort the transaction anymore at that point, because everyone has said by their best efforts, they expect that to be able to succeed. Now, what is the life of our applications? In management theory, it'll often be called a managed object because it's consuming config, it's providing operational data, it's being managed. You can think of it as simply your application that's consuming configuration information. So, you'll typically bring up your application. It will attach to the CDB API. It'll place any subscriptions to say if this data changes, please inform me. And it will also read out its initial configuration from CDB and then enter an event loop waiting for subscription notifications to be told that the configuration that it's interested in has changed. Now, there are various different calls available in the CDB APIs. You should consult the conft lib CDB man page in section 3 of the man pages for detailed information on the API calls that are available. But there's typically initialization calls like CDB connect, start session, set namespace. There are various CDB get calls corresponding to the type of the data that's being read in regards to the Yang data model types. So if it's declared to be a Boolean in your Yang model, you'll call CDB get bool in order to read that Boolean value from CDB. There's individual element read items, but sometimes it's more optimal in your system to do a bulk read. So there are calls such as CDB get object and CDB get values available in the API. Now, I should mention, so that you're aware of it, when you see the word object in the conft APIs, it is nothing to do with object-oriented programming objects. An object is a list entry from the Yang model, i.e. think of it as a row in a table. So anytime you see in the API calls that end in object or objects, those are talking about Yang list entries, i.e. rows in a table. Calls such as CDB get values is more of a scatter, gather, read capability where you can read disparate items that aren't necessarily in the same list entry. And there are other types of utility functions in the CDB API. So certainly you'll want to take a look through the detailed API information to understand the API calls that are available to you as you write your applications which interact with CDB. So, your application, when it's going to read its configuration from CDB, will first need to start a session to the database by calling CDB start session. CDB does have the concept of write locks and read locks on the data store. There may be a single write lock in place at any time, i.e. only one transaction may be actively writing to the database at the time. There may be any number of transactions being populated, but only one can be actively committing into a data store at the time. There may be multiple read locks. You may have multiple readers at the same time of CDB, but if there is a write lock in place, no read locks may be taken, and if any read lock is in place, a write lock cannot be taken. CDB start session, when you're reading, will take a read lock. There are variants of the API call where you can simply bounce and get an error return if you can't get the lock on start session. There's also API calls that allow you to spin wait until you can get the lock. When you call CDB end session or drop the socket that your API calls are going across, the read lock will finally be released. So your time between CDB start session and CDB end session should not be long. You shouldn't do anything long-lived processing. You should start your session, read your data, end your session, do your processing. If you accidentally call CDB start session, your program hangs, doesn't call stop session, doesn't drop the socket so that we know it's gone. There are timeouts running so that we can automatically get the system working again so that an application error can't crash conf D and cause problems with your element. Now, there's also the idea of namespaces within the data stores. Here, when you've done your startup of your session, you'll want to select which Yang data model, i.e. which namespace, you're going to want to read your configuration data from. So that is done, as you see in the code snippet at the bottom of the slide. After you've connected to CDB and started a session, you'll do a set namespace where that symbol, the second parameter of set namespace, is a hash code that refers to a particular namespace, in this case from a model called dhcpd.yang. That hash code that's used for that namespace selector is automatically generated by confd. Confdc, the confd compiler, will take your data model and generate this header files from which then you can use symbols to refer to the appropriate hash code. Now, when you want to read out configuration from CDB in the APIs, you will use key paths. A key path uniquely identifies an item in the data model. It is a path to that item. So, for example here, say we had a data model that was container DHCP, leaf default lease time. The path to default lease time is as you see it here. If you've worked with file systems, directories, files, paths in a Yang model are very similar to a file system because a file system's hierarchical, as is Yang. Now, you also in key paths need to provide key values if you want, say, for example, a specific entry from a list, i.e. a specific column from a specific row of a table. In that case, you introduce, as we do in the second example here, the curly brace notation in your key path, and your values of your keys go in between the curly brackets. If there are more than one key for a Yang list, you will list the multiple keys with space separation, and the keys must be in the order that they were declared in your data model. There are also some formatting directives similar to printf that are available in most of the confd API calls. So the second and third entry here, we can see %s and %x notation being used as format along with additional parameters. The ability to do this formatting makes certain processing easier when working with CDB. In addition to this curly brace notation for specifying keys in a key path, there's a square bracket notation available for indexing or walking. So that's this code snippet at the bottom of this slide is an example of that. We call CDB num instances against a Yang list called subnet to find out how many entries exist in that list, i.e. how many rows are there currently in this table. And then without knowing the key values, we can simply traverse that table calling by using, as we see in this path, the square notation, which also supports printf style formatting. So you could simply, if you were going to walk a list and just take it in whatever order, you'd call CDB num instances to find out how many instances are there. You'd loop on that return, and then could do something like CDB get object to read a row of the table and iterate through. Your application, after it's done reading its configuration, will also want to be told of any subsequent future changes of configuration which might occur, which concern it. That is where subscriptions come into play. Here, we'll use, after we've connected to CDB, we'll use the API call CDB Subscribe or CDB Subscribe 2. There are two variants of the API call. I won't go into the differences of them in this training module, but you can check the user's guide for more information. But in the subscribe calls, you'll have a priority level, a namespace selector, subscription points, and a path to where you want to subscribe. So in the case of CDB Subscribe here, we're subscribing to /DHCP. So the subtree below DHCP, if anything changes there, we're subscribed and will be notified of that change. ConfD and CDB will not notify your application of subscription changes until you tell us you're done subscribing. In order to avoid border race conditions where maybe you've got to place 4 subscriptions before your application is ready for processing, what would happen if you'd only had 2 of those subscriptions in place and a transaction commits that causes one of those to fire before you've registered your 3rd and 4th subscriber? So, as a result, to ensure a robust system, ConfD and CDB will not call your subscribers until after you've told us you are done subscribing and ready to receive subscription notices as a result. Once you've placed your subscriptions, you'll enter in an event loop to monitor the subscription socket that you're listening on for notifications. Typically, you'll monitor that subscription socket using either the poll or select system calls. So here we see an example of monitoring and polling on a subscription socket called subsocket. Once we see receive activity, we simply call the ConfD library with CDB read subscription socket, and from there we'll find out what subscriptions have fired. Now, there is, for example, the subpoints or subscription points and reslen or result length parameters on this call to read subscription socket. If a transaction causes a subscription notification to your application, and you have multiple subscribers at the same priority level that need to be triggered by that subscription, ConfD and CDB will only notify your program once. It will reslen, it will tell you how many of your subscriptions have fired, and subscription points will be a returned array that allows you to find out which of your subscribers have been triggered with this notification. Once you're done handling your subscription, you need to be called CDB Sync Subscription Socket to inform ConfD and CDB that you are done with your subscription processing. This needs to be done before we'll proceed to the next lower priority level and notify subscribers so that we know that it's safe to do. So again, in your subscription handlers, you really shouldn't do something that takes a lot of time. You should handle your subscription, sync it, and allow other subscribers to act upon the data. So with that, we wrap up this introduction to CDB. You've been introduced here to the basic theory and architecture of the CDB database. In the next module, we'll talk about how do you handle CDB subscriptions. Thank you.